Hey guys, it's Kevin at the Air Zoo, and I'm here with Arie Gunderson. Arie, I think this is your third time here for Spyposium.
Second, actually.
Second time, okay. And last time you gave us a great video about the Pratt & Whitney J58, and we're going to talk about a little more details and ask you some questions and let you tell us about the engine. So to get started, before we get rolling, for those who haven't seen the prior video, just give us a little introduction of your background.
Okay, hi. My name is Arie Gunderson. I worked for Pratt & Whitney for 33 years. Most of that was on the SR-71 program, the engine, this J58 behind us right here. I also worked on the engines that power the F-15, the F-16, the C-17, Space Shuttle main engine turbopumps, and worked a little bit on the proposal for the F-119 engine, which powers the F-22. I also got involved in foreign military sales. The last assignment I had was program manager for the Polish F-16s. When Poland joined NATO, they chose the F-16 powered by the Pratt & Whitney engine, and I was lucky enough to be selected to take over that program. I had a great time in my career at Pratt, and I'm also having a great time being retired.
Very good. I'm going to start out here in the front, and the first thing I want to ask is, can you explain these two devices here, as well as the next one that's down here, and this. If you could explain to us what those are, what they do, why they're important to the engine.
So one of the aspects of any jet engine is how do you maintain control of what's going on. So the most obvious piece of control is the throttle that the pilot has. The pilot's got a throttle typically on the left-hand side of the cockpit or left-hand side of his dashboard if it's a smaller aircraft. And the other significant thing that the engine wants to know is what is the temperature of the air that it is operating in. So in jet engine parlance, we call that the temperature of the air that's around the front of the engine TT2. It's station number 2. Station number 1 and 0 are out in front of the engine, in front of the airplane, respectively. But TT2 is total temperature. That's what the TT stands for. TT2 is the temperature right here at the face of the engine. And so all four of these devices that we're going to talk about are designed to be able to tell the engine what the temperature is of the air that it's using. So let's start off with these two right here that are located about 1:30 and about 3 o'clock. These two little devices here that are sitting in the airstream are actually a differential pressure device. And on the outside of this thing, there is a mechanism in there. There's a little flapper valve that is controlled on one side by a spring and on the other side by the pressure of the helium gas that is captured in the little tubes inside the gas path portion of that device. So as temperature goes up, helium expands very reliably and very significantly. And so the pressure that it exerts on the little spring ends up creating a delta P in the fuel that is coming in versus coming out on the outside of this sensor. The fuel control looks at both of these and picks the one that has the highest delta P, under the assumption that if one is reading significantly lower than the other, it's probably broke and would give us a false reading. In other words, tell the control that it's actually colder than it really is. So the control will always look at the highest delta P. In other words, the most accurate temperature. Over the course of the program, we had almost no failures or malfunctions of TT2 sensors. They're very, very reliable, mostly because they're pretty simple. The next device that you pointed out is this little tiny probe that's about as big as a pencil. In the very tip of this probe is a hole, and just inside the hole are 4 thermocouples. The 4 thermocouples actually have nothing to do with the engine. This probe is what feeds the inlet temperature to the cockpit of the airplane, so that the pilot knows what the temperature is that the engine is operating at. interesting, perhaps, you know, if you think about it, but it ends up becoming truly important because the speed limit of the airplane is temperature-based. It's not Mach number based, it's temperature-based. And so knowing what the inlet temperature is very, very important. Now, you may recall from the previous two years ago video, the speed limit on the airplane is a temperature, 427 degrees centigrade or 800 degrees Fahrenheit. And this probe is what tells the pilot how close he is getting to that limit.
And we're talking about the air temperature at that point.
Right, exactly. The air temperature that's going through this little hole.
Max 800 degrees.
Right. So we go back, let's think back to that other video. We got air coming in the front of the nacelle. It crosses a shock wave. When it crosses a shock wave, it goes into a higher pressure, it slows down, and it gets heated up. So it goes from minus 45 degrees, which is the air temperature at 80,000 feet. It goes from minus 45 to plus 800 as it crosses that shock wave. It goes from 0.4 psi, in other words, almost a vacuum, barely enough air. As it crosses the shock wave, it gets compressed up to just over 15 psi. So that's the air that the engine is seeing right at this point, about 15 psi and about 800 degrees Fahrenheit. So this next one, very, very similar on the inside. This little squat guy sitting right here, just like that last probe we talked about, it's a thermocouple, but its job is to send a signal over on this side of the engine to the afterburner fuel control so that the afterburner control has its own source of TT2 or inlet temperature. So all four of these probes sense the same temperature, but each of them has a slightly different purpose. We talked previously about, you know, what materials the engine is made of. The vast majority of the engine is an iron-nickel alloy called waspalloy, but the very front of the engine, the first stage of the compressor, the inlet case, and especially the first stage compressor blades are made of 811 titanium. And so, you know, that's part of the reason why we have a speed limit, is because this material is safe up to 800 degrees. It becomes notch sensitive higher. After every flight, you have to inspect for foreign object damage, or FOD. And so after every flight, we would take our smallest mechanic and put him in what's known as a bunny suit. This is a white coverall which includes booties, but no pockets. In other words, we don't want to drop anything out of a pocket when we're crawling up the inlet of the airplane. So we send this little guy up, and he squeezes underneath the spike and crawls up close enough. He does in fact have a monocular with a flashlight built into it. And what he does is to look at each first stage blade, while another mechanic is outside the nacelle with a crank on the bottom of the engine, and that crank is being turned to rotate the rotor. The X is on there to provide us with a starting and end point for that post-flight inspection. So what he's doing with the monocular is to look at both at the leading edge of each blade, looking for irregularities. It should always be a straight line, but it's possible that we may have picked up a stone or something like that during takeoff or landing and created damage along the edge of the blade. That's a stress riser, and it needs to be fixed. Now, in the event that he does find something, now we've got to bring him back out, hand him a set of files and a flashlight, actually a hot light, and we send him all the way back up again, and this time he's got to crawl right up into this space right here and work on the blades with a set of files to remove the damage and blend it out so that it's smooth.
And so the X is his starting point to go all the way around and make sure he's covered every blade.
He has to look at each of these 34 blades.
We often get asked, what's the X? And people think something's defective.
No, it's just the starting point.
Gotcha.
Now it's painted with an aluminum-based paint. so it doesn't interfere with the titanium. Titanium is an interesting material in that certain other materials cause it to become sensitive. Cadmium, for example. You would never use a cadmium-plated tool on anything made of titanium. Absolutely forbidden. Isn't a big deal as long as everything stays cold, but it becomes a really big deal when things get hot. The cadmium causes cracks just from a catalytic chemical reaction.
These are, as I understand it, bleed bypass tubes. Can you tell us a little bit more, why are these here, what their function is, and I'll let you take it from there.
Okay, so the J58 is basically a very simple single spool turbojet. 9-stage compressor, a can annular burner system, 2-stage turbine, and an afterburner stuck on the back end. Very, very simple device. And probably could get up to Mach 3 all by itself without the aid of any bypass tubes or changes in the operation. Just muscle its way up there, just like the MiG-25 does. Getting to Mach 3 is not a big deal. Get enough horsepower and you can get a barn door up supersonic too, right? So, but in order to be able to cruise at Mach 3, in other words, to fly steady state for an hour or so at a time, you've got to have a little bit more finesse in the game. So the finesse comes on this engine by trying to figure out how you're going to use all of that air to the best advantage and become economical when you're at cruise. So the way we decided to do that, a friend of mine who passed away a couple years ago actually came up with the idea for this, but Dr. Bob Abernathy was his name, Pratt and Whitney guy, very, very smart guy, and he's the one who invented this bypass system. And what the system consists of is we knew from testing on our heated inlet test stands that when we were at the Mach 3 conditions and 80,000 foot conditions, that the front end of our compressor was not getting enough air. The back end was being overloaded. So we had two opposite things going on. We had stall starting to happen in the front and surge happening in the back of the compressor. It turns out that the solution to this issue is to bleed away a little bit of the air. And so we put 24 doors around the 4th stage of the compressor and hid those doors underneath this duct. And at Mach 2 or so, the inlet guide vanes shift to a cambered position to help limit airflow coming in, and these 24 doors open up and start to bleed air through these tubes from the 4th stage of the compressor and allow the air to re-enter just aft of the turbine and in front of the afterburner. This creates the beginnings, at the Mach 2 area, the beginnings of a ramjet cycle, because the afterburner is operating continuously. So now we're adding more air. It does two things. It provides not only the combustion air that we need to achieve the ramjet phenomenon, but it also provides additional cooling air for the ducts that are containing all of this stuff. Keep in mind that in the afterburner, we're talking about flame temperatures that are around 3,500 degrees, stoichiometric burning temperatures. Pretty amazing stuff.
And just to interrupt, when we talk about cooling air, tell us, what is the actual temperature of this air that we're calling cooling air being fed into the afterburner?
Okay.
Cooling is a relative term, I get it.
Cooling is a relative term, and the way we figure it in rough terms, each stage of compression raises the pressure by about 50 psi and the temperature about 50 degrees Fahrenheit. So we're at the 4th stage, so we've added about 200 degrees. So this is 1,000-degree air. But it's on the back end, that is indeed cooling air. So this starts at Mach 2. As we go faster and higher, the proportion of air that's being bled back to the afterburner increases relative to the gas turbine portion of this. And by the time we get to Mach 3 or so, the gas turbine portion of this engine is not doing very much work at all. It needs to keep rotating because it's powering the aircraft gearbox, which is the hydraulic power for the airplane and the electrical power for the airplane are all being generated off of a power takeoff shaft down here on the bottom of the engine. So that's what the tubes do. They're the thing that provides the cooling air and combustion air for our created ramjet. One of the things that is a function of an engine on any airplane is it has to help power the systems of the airplane itself. And so in order to do that, you have to have some sort of mechanical power takeoff shaft. So that's a gearbox, right? So you got a gearbox on the bottom of the engine that powers the main fuel pump and the oil pump and the oil pressure, the tachometer drive, all those things. But it's also got a shaft that's coming out to a reduction gearbox down here, and then attached to that reduction gearbox is a drive shaft that goes to the aircraft ADS, accessory drive system. It's another gearbox, and attached to that gearbox are the aircraft generators and the aircraft hydraulic pumps. Now this shaft that is down here, we call it the Bendix shaft. It was made by the Bendix Corporation in Indiana. That shaft has two carbon universal joints on it and the flanges. And when we install that shaft, it's got a 2.5-inch offset at sea level normal conditions like we're standing in right now. What that tells us is that the engine actually, when it's up at cruise conditions, the engine grows 2.5 inches in diameter, and that shaft ends up running straight and true with no offset whatsoever. That's how much we're dealing with thermal expansion on this engine. The shaft itself is transmitting about 250 horsepower, and that's what is powering the aircraft systems, one on each side. So the aircraft needs 500 shaft horsepower to run its electrical and hydraulic systems.
We're back on the side of the engine, and one of the things that often comes up is, didn't they use gold in the aircraft? And you can see flashes of a gold tint here. Can you explain to us what they were trying to do and what eventually occurred?
All right. So when we first built the engine, we had pretty much carte blanche from our what we call customer number one. Hint, that's the CIA. We didn't know how far we had to go to get everything achieved. We all knew that gold is an excellent conductor not only of electricity but also of heat. And so our initial put on building this engine was to gold plate some of the items on the engine where heat was especially sensitive. Things like the oil tank on the other side of the engine, the fuel oil cooler, most notably here on this side, and some of the tubes that were carrying fuel or oil where temperature was a huge consideration. Testing that we performed after we had actually incorporated this on the prototype versions of the engine showed that there was indeed a benefit to having the gold on the outside of the components, but the effect was minimal when it came down to the practical side. Do we really need to drop the temperature of this article by 2 or 3 degrees? Or could we get by without the gold and live with it those couple of degrees hotter? The answer turned out to be yes, we don't really need the gold. And it also turned out that it was going to be way more expensive to recover the gold than what it was actually worth. So we just left it alone, and as it wore away, and we didn't worry about it. So that's why you see some engines with gold on them, and in a lot of places it looks like it's worn out. It's fine. It's 1 or 2 atoms thick. We're talking about a seriously insignificant amount of gold.
Next we have here this container. I believe you talked about the way it starts with a chemical ignition system, but I thought it might be interesting for you to talk a little bit more about this container and also where this chemical, triethylborane, gets fed into the combustion chamber and afterburner. So if you could talk about that a little bit more.
Triethylborane is a pyrophoric fluid. It burns at about 3,000 degrees immediately in contact with oxygen or with air. And the triethylborane is used as a starter fluid on the J58 engine. Several rocket engines also use it as a starter fluid as well. So a rocket engine, for example, would have in the fuel line that enters the combustion chamber, there'd be an ampule of triethylborane in it, and when ignition is ordered for the rocket engine, that ampule is shoved out into the combustion chamber, it bursts and starts the fire that needs to be in the rocket engine. So we have a similar thing that goes on here with the J58 engine. JP7, our fuel that we used to operate, is highly refined kerosene with extremely low vapor pressure. And as a result, it won't burn unless it's above 165 degrees. Now, as we go through the pumps and stuff and we work our way through the engine to get to the burner section with fuel, the fuel is hot enough to burn at that point. And if only we were going to do was be subsonic, ordinary igniters, spark plugs in automotive terms, but regular jet engine igniters would actually work fine if we were never going to go supersonic. But we do go supersonic, and so as a result, electronic things don't work when they get really, really hot. So we have to have another way of starting the engine. And so what happens is, as we spin up the engine, either with an air cart or with a Buick cart or whatever, and we spin it up at about 3,000 RPM, the guy running the cart tells the pilot, okay, you can initiate the throttle. The pilot moves the throttle from cutoff up to idle. The fuel control here senses that movement. Here's the mechanical connection to the throttle up in the cockpit. It sends a signal up here to this, which is where the TEB is stored. Then opens up a valve and it sends 15 to 18 cc's of TEB into the number 8 burner can to initiate combustion in the burner section of the engine. The burner cans are designed with crossover tubes so that the flame can propagate around the entire circumference of the engine, and the burner cans are also designed for a self-sustaining flame front. Once we start the engine, we don't really need any more TEB in the main engine because it's a self-sustaining flame front. Unless we blow the engine out, unless we flame out or something like that, and you have to do a restart. That's why we've got a large container of TEB. You never know when you're going to have to restart your engine, hopefully before you get to the ground. Afterburning works the same way. Attached to this same tank is another tube that runs back over here to the back end of the turbine and in front of the afterburner. And so when the pilot wants to light off the afterburner, he moves the throttle up to about 88 degrees power level angle, and that initiates afterburning. So now we've got fuel flowing into the afterburner, and we send a shot of TEB right in front of where the fuel is flowing, and that gets the afterburner started. Just like the main engine, the afterburner is designed for self-sustaining flame front, but to back that up, if we can walk around the back of the engine, one of the safety features that we built into the engine, and if we'll get a light, but you see these white rings inside here. The white rings have got some little tiny round circles in them. So if we look in here, we can see these white rings. Those are called flame holders. And in front of each flame holder is a spray ring. The spray ring is what's providing the fuel to the afterburner. The flame holders create the aerodynamic disturbance necessary to hold the flame close to where the fuel is being emitted. In the event of a blowout back here, or another way to back up lighting the afterburner, each of those little tiny circles that you see embedded in there contains a very small piece of platinum grid, and it provides a catalytic ignition to the fuel. Now, sometimes the pilot will go into manual trim and he'll push up the EGT a little bit. That's exhaust gas temperature. He'll push up EGT to make the catalytic igniters glow a little brighter. The only time he would do this is if he has actually run out of TEB. It would take an exceptionally long mission for you to actually run out of TEB But in that event, those catalytic igniters provide us the backup we need to still be able to operate the afterburner. In our afterburner, the afterburner ducts themselves, the liners, the duct on the outside is waspaloy. The liners are a hastelloy material. Again, I'm tossing off these exotic names, but there's one or two people will actually bother to look that up. But that in itself gives us not so much the strength, but strength at temperature. Now, even with that, using this special alloy, we still need a ceramic coating on the inside to help further dissipate heat. Now, one of the things that you've got in your home right now is a self-cleaning oven. Your self-cleaning oven at home has got a ceramic coating on the inside. In most cases, it's black. It's not this creamy white color. You know, every time you cooked a lasagna, you'd have a mess to clean up, and you'd have to run your oven through a self-cleaning cycle. Well, we do a self-cleaning cycle every time we start the afterburner. What you're looking at here, this white material or cream-colored material, is a substance known as magnesium zirconate. It's a ceramic. It gets applied with a flame spray process. When we set the duct up to be recoated, it's sitting vertically, and then we stick the gun up in the middle, and the gun rotates and sprays out the molten ceramic to a uniform thickness around the inner surface of the duct. The actual surface area of the ceramic is significantly higher than what it appears to be. That's how your self-cleaning oven at home works too. So let's say we've got a 1 square foot surface of your self-cleaning oven or my afterburner duct sitting there. The actual surface area is 3 to 5 times greater. What that means is that when it gets hot, we have that much more surface to radiate heat out.
I know you get this question a lot. I heard it the last several days. A couple of things. If you could talk about the temperatures that you experience back here in the afterburner, and also how that area here relates to the overall expansion of the aircraft, because when you talk about expanding 6 inches, I think a lot of people look at these and question, how is it doing 6 inches, and you have a way of explaining where are we getting the expansion,
right,
and also what do we have to deal with temperature-wise
right
here.
So we've already talked a little bit about the fact that the engine increases in diameter by 2.5 inches, and there is axial growth as well. It's all getting hot, but back here we're talking about really, really hot. So we know from looking at the outside of the bypass tubes, this back end, they've got these corrugations in them, and the corrugations are designed so that we can absorb thermal growth. There's gaps in the bolts that are holding them in place, and so we can gauge pretty much how much growth is going to happen. Now that is even a little bit misleading, because the bolts themselves are increasing temperature-wise as well. But when we put all this stuff together, we leave about a 1/2 inch of gap in those bolts to make sure that the bypass tubes are properly captured and guided to where they're going to go. Now the back end of the engine, the skin temperatures are what we're talking about. All of these various parts back here, skin temps are going to be up in the 2,000 degree range. Pretty amazing when you think about having strength at temperature, which is why we end up using waspaloy and hastelloy and some of these alloys that are the very, very few we have to work with that have strength at temperature. So material selection is very, very critical if you were going to try to duplicate what this J58 engine does. Some of the pictures that you may have seen of this engine when it's operating at max AB, these ducts get so hot, so red hot, they become somewhat translucent in the fact that you're seeing heat shadows of all the parts that are underneath the skin. Pretty incredible to think that even though you can perceive that you're looking through this stuff, it's so hot, that it is actually strong enough to contain all the force associated with cranking out over 32,000 pounds of thrust. Now, the other aspect of what you asked me was the growth associated with that. So the average, and this is my calculation, the average growth of what I think this thing does is somewhere between 4 and 6 inches of total growth in the length of the engine. The engine at the center hanger mount is fixed inside the nacelle. So there's a minor amount of growth on the front end where the compressor is, and most of the growth that I'm talking about occurs here on the back end of the engine, because that's where it gets hot. That's where the greatest delta T change in temperature is occurring, and so that's where we're going to see the majority of growth. And since everything is expanding pretty much at the same temperature, the growth with each layer of material in this thing is pretty much uniform. The bearings even are designed to accommodate the thermal growth of the rotor. So the center bearing, the main shaft bearing, is fixed. It's a duplex ball bearing, and that's where the thrust is transferred from the device into the airframe. But the number 1 and the number 3 bearings here are rollers to accommodate thermal growth, but still allow the turbine and the compressor to remain centered in their operation. And as you might guess, the tolerances that we allow for these bearings when they're manufactured and overhauled is very, very tight. Very closely held. The dimensions are down in the 10,000ths and in some cases the 100,000th of an inch. Amazing, again, when you think about when we did all of this engineering work.
So Arie, I understand in the SR-71 we have mice on board. Can you tell us about the mice on the aircraft?
Yeah, what we're talking about is not Mickey Mouse, and we're not talking about having to call the pest control company. What we're talking about is boundary layer control. So what does that mean? It means that air that's flowing over a long flat surface has something known as a boundary layer. That boundary layer can be just a few thousandths of an inch thick, and it can be very, very smooth. If you think about the water that's going past a canoe, when you're out in a canoe and you're paddling, the water is running past the side of the canoe, and it's very, very smooth. That's known as laminar flow. And on the very leading edge of the lip of the inlet, we have, for just a very short distance, laminar flow. It makes a transition to turbulent flow. But turbulent flow is what we're actually after because there's less drag associated with turbulent flow than laminar flow. But we still want to be able to control to make sure that we don't separate the boundary layer from the surface, because that will then create uncontrolled turbulence, which ends up at the front of the engine and makes the engine go unstable. So managing the smoothness of the airflow is very, very important. In the early days of the program, when we were first designing the inlet system, we had a couple of ridges, which we can take a look at, that they look like little knife edge separation points that would peel off a section and reestablish laminar flow again and the boundary layer. That turned out to be not enough, and especially when we became high-speed supersonic. And so we purposely put in this series of long humps. They're about this long. They look like a little hump in there. It looks kind of like not a mouse, but like a lump. But they ended up calling them mice. And so there are a series of mice around the circumference of the inlet aft of one of the boundary layer control devices to help induce the controlled turbulent flow that we need for smooth, even velocity air coming into the front of the engine.
Very good. One other thing that I'd like to ask, because you talk about this often, is in the rear you have what's called a, if I'm saying this right, convergent-divergent nozzle. And that's actually very important for what's going on here. So could you tell us a little bit about that?
Right. So when we think about an engine that's mounted on an airliner, for example, we think about the nacelle, and the vast majority of the nacelle is the whole engine. There's a little section on front which has got the cowl, and you know, it's got the smooth part, and you can put your logo there and all that sort of stuff. That's all wonderful if you're going to stay subsonic. But if you're going to go supersonic and you want to be able to cruise at Mach 3 efficiently, you need to be able to capture all of the energy that's coming in the front. When you compress and heat that air in the front, use the air, this becomes the pump that's giving you all the muscle necessary to keep the air flowing. Coming in the back of the engine, we've got all the air that we had in the front, which got separated, by the way. About a third of the air at cruise is going through the engine. Two-thirds of the air is going around the outside of the engine, but it stays inside the nacelle. If you dump that air overboard, it creates drag. So a lot of the airplanes we're familiar with can go really fast. This F-18, the F-14, whatever else you've got here, have got ramps built in to dump off that excess air that their engine can't use once they go supersonic. That creates drag, and it's one of the reasons why they can't spend a lot of time being supersonic. We need to spend time being supersonic, and so we have to capture the energy. The engine is pumping the air through the whole nacelle, but we got a lot of air going around the outside that we put a lot of work into. Remember, we took it from 0.4 psi and minus 45, and we pumped it up to 15 psi and 800 degrees. That took a lot of work. Let's not lose it. So all the way at the back end of the engine, if we look over at the airplane, you can see those little flapper doors that sort of sit at the back end of the nacelle. Inside that area is a convergent-divergent duct where these two airflows get combined again. The exhaust of the engine and all the air that's going around the outside of the engine, but inside the nacelle, rejoin and pass through a convergent-divergent nozzle. This is very, very important because that's how we achieve supersonic flow. In order to get about a Mach 3.5 exhaust gas velocity, we have to have a 40-to-1 pressure ratio across that convergent-divergent nozzle. Now, in the video that I made a couple of years ago, I made a math mistake, which I will not repeat. So there was a lot of comments about that on YouTube, but nonetheless, what we're talking about is the outside air pressure, as I reminded you before, is only 0.4 psi at 80,000 feet. So we only need to have about 160 psi in front of the convergent-divergent nozzle to achieve a Mach 3.5 exhaust gas velocity. So that's not a lot. I mean, it is when you think about how big the afterburner is, you know, to have a pressure in there of 160 psi or even a little bit more, because you always want some cushion, right? Getting all that stuff together and squeezing it out through the nozzle. You can approximate something like this at home when you think about your garden sprayer. Your garden sprayer with a little bottle of insecticide at the bottom. You've got the jet of cold water coming out of your tap, and then you pull down the little air hole on the top, and it sucks all the insecticide or the fertilizer or, you know, whatever you're going to do. It comes out through the bottle. That same thing is happening here at the back end. So with the flow that's around the outside of the engine. The engine itself is the primary mover. It's your garden hose. And then the air that's from around the outside is equivalent to the insecticide or the fertilizer, and it's getting drawn through. That's where the muscle comes from to provide that pressure ratio across the nozzle.
Arie, I can't thank you enough for the time you spend here at the Air Zoo. But for those who want to see you more than just the Air Zoo, where can they visit you?
So during the summer months, I'm in McMinnville, Oregon, at the Evergreen Air and Space Museum, which is home to the last SR-71 that actually flew, as well as the Spruce Goose. It's located about 30 or 35 miles south of Portland, Oregon. And I would sure enjoy seeing any of you show up on a Friday during the summertime, and I'll be happy to give you a guided tour.
Thank you again.